Hello, I am Remy, or the physicist, and today the physicist will be talking about waves and sounds, which is our outcome for this term. So we will also be talking about how waves and sounds and the interaction of waves and sounds can be impactful and is able to be demonstrated by the user or the audience. So the outcome for waves and sound is able to implement phenomena of waves and lights in a physical and geometrical optics phenomenon to provide a future forward innovation. The big question is, why might visionary leaders cause and or affect transformation? And this will be answered in today's video. And in today's video, I will be covering the two different waves interactions, which are reflection and refraction. So I'm going to start by explaining to the user or the audience what is reflection. So in the context of physics, reflection is the change in direction of a wavefront, such as light or sound, when it encounters a surface or a boundary that does not absorb the energy of the wave and instead it bounces it back. So this phenomenon occurs according to the law of reflection, which is that the angle of incidence, or the angle at which the incoming wave strikes the surface, is equal to the angle of reflection, which is the angle in which wave leaves the surface. So a real-life example of reflection is seeing yourself in the mirror. So when light waves hit the smooth surface of a mirror, they bounce back and create a reflected image. That's how a mirror works. This is due to the light reflecting at the same angle it hit the mirror, allowing you to see a clear image of yourself or any object in place in front of the mirror. An example of reflection being applied into our real life, so the user can apply it, is like rear view mirrors. So rear view mirrors exemplify the physics of reflection. Light from behind the vehicle strikes the mirror's surface and reflects it into the driver's eyes, adhering it to the law of reflection. These mirrors, positioned inside and outside the car, aid safe driving by providing a clear view of traffic behind and reducing blind spots, so we can see all around us, behind us, and different parts of where behind us, like directly behind us or behind us to the right, behind us to the left. So basically, rear view mirrors are really important. For the second topic, we have diffraction. So diffraction is the bending and spreading of waves when they encounter an obstacle or pass through a small opening. So the effect is most noticeable when the size of the obstacle or opening is comparable to the wavelength of the wave. It happens with all types of waves, including light, sound, and water waves. So diffraction has several everyday applications and effects, including sound, light, radio and TV signals, holograms, and gratings. So for sound, when you hear someone or someone speaking around the corner, the sound waves are bending around the obstacle due to diffraction. So for example, when you open a door slightly, the sound waves will bounce and will spread across the room, and it will be much quieter than when the door is fully opened. For light, the colorful patterns seen on CDs or DVDs are caused by light diffraction off of the closely spaced tracks on the disc surface. For radios and TV signals, radio waves diffract around buildings and obstacles, allowing signals to reach receivers that are not in the direct line of sight of the transmitter. For holograms, diffraction is used to create holograms, which store light patterns to produce 3D images. And for gratings, diffraction gratings are used in devices like spectrometers to separate light into its component color analysis. These are just a few examples though. So diffraction is used in various real-life applications across different fields. Some notable examples include optical instruments or X-ray crystallography. So for optical instruments, diffraction gratings are essential in spectrometers and other optical instruments to separate light into its constituent wavelengths for analysis in fields like chemistry, physics, and astronomy. And for X-ray crystallography, this technique uses X-ray diffraction to determine the atomic structure of crystals. It is crucial in fields such as biology, chemistry, and material science for the study of structures of proteins, DNA, and other complex molecules. This is my voice when the door is open, and this is my voice when the door is closed. And to answer the big question, which is how can visionary leadership cause and or affect transformation, in the context of physics, visionary leaderships can cause and affect transformations in various ways. but I'm just going to name a few. So, for example, in research and innovation, visionary leaders in physics inspire researchers to explore new frontiers, challenge existing paradigms, and pursue groundbreaking discoveries that can revolutionize our understanding of the universe. For investment in technologies, visionary leaders advocate for investment in advanced technologies and infrastructure, such as particle accelerators, telescopes, and space exploration missions, driving progress in innovation towards physical research. And that's going to be all for today. I hope the physicist was able to convey information to the user or the audience. Thank you.